colloquium and the first Rademacher lecture of the week. We're fortunate to have Dr. Jacob Lurie from Harvard University with us, and to mention just a few of his distinctions that I wanted to mention. As an undergraduate, he won the Morgan Prize for his thesis on Lie algebras. In 2004, he received his PhD from MIT for a thesis on derived algebraic geometry. And in 2014, he received a couple of notable prizes that received the Breakthrough Prize in Mathematics. It was also named a MacArthur Fellow. And the talk today is titled The Siegel Mass Function and Bayes Conjecture.
All right, thank you very much, and thank you for inviting me to give these lectures. So what I'd like to talk to you about eventually in this lecture series is some joint work with Dennis Gatescory about function field analog of Bayes conjecture for Tomogawa numbers. And what I would like to do in this first lecture is just set the stage by explaining what Bayes conjecture is about and why you might be interested in it. So let me start by talking about quadratic forms. By quadratic form, I just mean a homogeneous quadratic polynomial in some number of variables. So here are some examples of quadratic forms in two variables. And one of the most basic questions that you can ask about quadratic forms is whether or not they're equivalent, meaning can you make a linear change of coordinates that transforms one into another? And the answer to that question will depend in general on what ring you're working over. So for example, the quadratic forms that I've written for you here, the coefficients that I've used are all integers, which means that I can regard these as quadratic forms with coefficients in any commutative ring that I like. So if I think about these as quadratic forms over the complex numbers, then they're all equivalent to each other because I can trade an x squared for a minus x squared by multiplying x by a square root of minus 1. But if I think of these as quadratic forms over the real numbers, then they're not equivalent to each other. Because, for example, this one on the left is positive definite. It takes only non-negative values. This one on the right is negative definite. It takes only non-positive values. And this one in the middle is indefinite, meaning it takes both positive and negative values. So these quadratic forms are not equivalent over the real numbers, and in particular, they're not equivalent over the integers. So let me give you another example. X squared plus y squared, and say x squared plus 7y squared. So these are, again, quadratic forms with integer coefficients. And over the real numbers, these are equivalent to each other, because you can multiply y by a square root of 7. But over the integers, they're not equivalent. And one way that you can see that is to see what happens when you reduce them modulo 7. When you work mod 7, this quadratic form on the right becomes degenerate. You could ignore the 7y squared, and it depends only on one of the two variables. But the one on the left is non-degenerate mod 7. So these quadratic forms are not equivalent mod 7, and therefore they can't be equivalent over the integers. So what I've just given you is two strategies that you might use if you wanted to prove that two quadratic forms over the integers are not equivalent. One strategy is to see what happens over the real numbers. And over the real numbers, quadratic forms are easy to classify. They're determined by their signature, meaning the number of plus signs and the number of minus signs when you diagonalize them. And another strategy, if you want to tell quadratic forms apart, is see what happens when you reduce mod 7, or mod 2, or mod 3, or mod any number that you like. And that has the virtue of at least reducing to a situation where there's only finitely many possible changes of coordinates to consider. So the story that I'm going to tell you begins with the question of whether or not these two strategies are sufficient to tell apart all inequivalent quadratic forms. So to make this precise, let's introduce a definition. So let Q and Q prime be quadratic forms. And let me just say, if I don't specify in this lecture, my quadratic forms all have integer coefficients. They're always going to be positive definite. And they're always going to be, when I mention two of them, in the same number of variables. So with that said, we say that Q and Q prime have the same genus if they are equivalent, not necessarily over the integers, but they're equivalent mod d for every positive integer d. So quadratic forms are in the same genus if you can't tell them apart by the two strategies that I described. You can't tell them apart over R because they're all positive definite, and you can't tell them apart mod n for any n. And so you can ask the following question: if you have two quadratic forms in the same genus, do they have to be equivalent to one another? And the answer to that question turns out to be no, but almost. If you fix a quadratic form Q and ask how many quadratic forms are in the same genus as Q, up to equivalence, well, up to equivalence, there's only finitely many of them. And in fact, there's a formula which tells you how many of them there are, provided that you count them with the appropriate multiplicities. So I want to state that formula for you, but first I need to introduce a little bit of notation. So let's say that Q is a quadratic form. R is a commutative ring where Q has its coefficients in R. I'm going to write OQ of R for the orthogonal group of Q over the ring R. So what this means is the set of all n by n matrices, where n is the number of variables which carry this quadratic form to itself. So this is a familiar object when Q is positive definite and you're working over the real numbers. So OQ of the real numbers, this is the usual orthogonal group of rotations and reflections in Euclidean space. In particular, this is a compact Lie group. But another interesting thing that you can consider when Q is defined over the integers is OQ of Z, which naturally sits inside here. So this is all rotations and reflections in Euclidean space. And this is the subgroup consisting of rotations that preserve a particular lattice in Euclidean space. And this subgroup is finite for a positive definite quadratic form, because if you look at each lattice vector, there's only finitely many places it can go, because it has to go to another lattice vector having the same length. So this is always a finite group. And that permits us to contemplate the following quantity, which I'll call the mass of Q. The mass of Q is a sum over all Q prime in the genus of Q of 1 over the size of the orthogonal group of Q prime. And this sum is taken over all, I should say, equivalence classes of quadratic forms in the genus of Q. So what is this sum doing? If you ignore the denominator, I would just be counting the number of equivalence classes of quadratic forms in the genus of Q. But these denominators here, meaning you're counting them with multiplicity, where the multiplicity is 1 over the number of symmetries that that quadratic form has. And this is a very natural way to count objects when those objects have some symmetries. One reflection of the fact that it's a good idea to count things in this way is that there's actually a formula for what this quantity is. So that formula is called the Smith-Minkowski-Siegel mass. And it says something like this. So Q, a quadratic form, again, over Z integer coefficients and so forth. Over Z and positive definite. And the Siegel mass formula says that the mass of Q is equal to something. Of course, this is not a complete statement of the Siegel mass formula. Anyone could have told you that, but it's equal to something specific. The something specific is a little bit complicated, so I'm not going to tell you what it is in complete generality. Let me just tell you what it is in the simplest case, and the simplest case is already very interesting. So For this, I need one more definition. A quadratic form Q is said to be unimodular if it is non-degenerate mod P for all primes P. And just a warning, none of the quadratic forms that I've written down so far are unimodular. So for example, you might think a quadratic form like x squared plus y squared, that's as nice as a quadratic form could possibly be, except not mod 2, because this is congruent to mod 2 to x plus y squared. And therefore, mod 2, it's really a degenerate quadratic form. After a linear change of coordinates, you can eliminate one of the variables. So being unimodular is actually a pretty strong condition. And so this is not obvious, but if Q is unimodular and positive definite, this implies that the number of variables is divisible by 8. So simplest examples of unimodular quadratic forms that you can write down, at least if you want positive definite ones, need to involve at least 8 variables. So another thing which is not obvious is that these unimodular forms comprise a genus. So it's clear from the definition that if I give you two quadratic forms, Q and Q prime, which are in the same genus, then Q is unimodular if and only if Q prime is unimodular. Because if they're in the same genus, they look the same mod P. But what's not obvious, but still true, is the converse of that. That if you fix the number of variables, then the unimodular quadratic forms in that number of are all in the same genus as one another. So if the number of variables is divisible by 8, there's this distinguished genus of quadratic forms occupied by the unimodular ones. And that's the case that I want to consider. That's somehow the simplest genus. So let's talk about what the mass is in the unimodular case. So assume that 8 divides n, where n is the number of variables. So on the left-hand side, I'm going to take the mass of the unimodular genus. So it's a sum over all unimodular quadratic forms in n variables of 1 over the size of OT of C. And again, there's one term in this sum for each isomorphism class. And this mass formula says that this is equal to a product of some special values of the Riemann zeta function divided by some volumes of spheres. Volume of the 1 sphere times the volume of the 2 sphere times the volume of the 3 sphere, all the way up through the volume of the n-1 sphere. So this is sort of an amazing statement. It's not necessarily obvious even that the right-hand side is a rational number. The numerator and denominator of these expressions are not independently rational numbers. They both involve some powers of pi. If you know something about special values of the Riemann zeta function, maybe it's clear that those should all cancel and that this should be rational, but this is saying not only is it rational, it has a very specific interpretation in terms of counting quadratic forms. So I want to give some examples of what this is saying. So the simplest example is when n is equal to 8. And in that case, you can evaluate the right-hand side explicitly. And what you get is 1 over 2 to the 14th times 3 to the 5th times 5 squared times 7. And if you really like exceptional Lie groups, you might recognize that number. That number is the order of the Weil group of the largest exceptional Lie group E8. And so this is 1 over the size of a certain, sorry, 8 got turned upside down. 1 over the size of a group which actually arises for you as the automorphism group of a particular lattice which is equipped with a unimodular quadratic form. So this group is actually one of, or this fraction is one of the terms which appears on the left-hand side of this expression. And so the mass formula, what it's telling you is that there can't be any other terms which appear in this expression. So the mass formula says there's only one unimodular quadratic form in 8 variables up to equivalence. So this example is potentially misleading because it might lead you to think that the equality that's taking place in the mass formula is an equality between quantities which are small. But another example worth thinking about is, say, when n is equal to 32, and in that case, the right-hand side is approximately 40 million. So the mass formula is telling you the right-hand side is equal to the left-hand side, which is a sum of quantities, each of which is less than 1. And if you want to get to 40 million by adding quantities that are less than 1, you have to use a lot of terms. So a consequence in this case is there exist millions and millions of inequivalent unimodular quadratic forms in 32 variables. So unimodular quadratic forms, in 8 variables there's just 1. In 16 variables you can prove up to equivalence there's 2. In 24 variables, famously, there turn out to be exactly 24. In 32 variables, there's no hope of ever classifying them. There's just way too many. Okay, so what I would like to do now is explain to you a reformulation of this mass formula using ideas that were introduced by Tamagawa and Gray. So I want to start by trying to do something we won't succeed in doing. Namely, I want to try to prove that unimodular quadratic forms in the same genus are equivalent. So let Q and Q prime be in the same genus. So I'll try to prove they're equivalent. I'll fail, but I'll fail in a way that gives some information. So what does it mean that they're in the same genus? Well, it means that they're equivalent mod d for every d. So first thing I can say is that Q can be written as Q prime composed with A sub d for some A sub d in invertible n by n matrix, which is defined mod d. And when I say equality here, I mean as quadratic forms over the ring Z mod d. So this has to happen for every d. And in this case, the first thing to observe is that these ADs can be chosen in such a way that they're all compatible with one another. So that, for example, when you take A9 and reduce it mod 3, you get A3. And that follows from a compactness argument given that there's only finitely many choices for what each individual AD can be. So without loss of generality, these are compatible. And compatibility means that I can consider the collection of all of these ADs. And I can view this as an n by n matrix whose coefficients lie in the ring that I'm going to denote by z hat. This is the ring of profinite integers. So z hat just means the ring that you get by taking the inverse limit of z mod d as d varies. Now this ring has some other descriptions which will be convenient. So by the Chinese remainder theorem, another description of this is it's a product over all prime numbers p of the p-adic integers, where the p-adic integer means you take the inverse limit of z mod p to the k as k goes to infinity. So going back to our quadratic forms, they're equivalent mod d for every d, and what we just said is this implies that they're equivalent over this ring z hat. So in particular, they're equivalent over the p-adic integers for every prime number p, and therefore they remain equivalent when you take the p-adic integers and invert p. And when you do that, you get a ring which is called the p-adic rational numbers, or a field which is called the p-adic rational numbers, QP. So let's say this implies that q and q prime are equivalent over each of these fields of p-adic rational numbers for every prime p. And let me just mark they're also equivalent over the real numbers because I assume that they were both positive definite. So now I want to invoke a non-trivial fact, a sort of central theorem in the arithmetic of quadratic forms, is the classification of quadratic forms over the rational numbers. So Hasse-Minkowski theorem asserts that if you have two quadratic forms over the rational numbers, they're equivalent if and only if they're equivalent locally, meaning they become equivalent after passing to every completion of the rational numbers. But to test if quadratic forms are equivalent over q, you just have to test over qp for every prime number p, and also over r. And q and q prime pass these tests. So what does this mean? Well, q and q prime are now equivalent over the rational numbers. And just remember what that means. That means that we can write q as q prime with coordinates changed, where b, our change of coordinates, is an invertible matrix with rational coefficients now. So now we're in a situation where q and q prime can be identified with each other by two different coordinate changes, using this matrix A and using this matrix B. And whenever you're in a situation like that, it means that you have a symmetry of q and q prime independently. So q, let's write that as q prime composed with A, but that's also q composed with B inverse composed with A, which means that this B inverse composed with A, this is a linear transformation that preserves the quadratic form q. Except, what kind of a symmetry is it? Right? A is a matrix whose coefficients lie in this ring z hat, and B is a matrix whose coefficients lie in the rational numbers. Now, if you want to multiply them together, you're allowed to do that, but you have to pass to a ring that contains both of those, both the rational numbers and z hat simultaneously. So there is such a ring. It's called the ring of finite adels. And it's just defined to be what you get when you take z hat and tensor it with the rational numbers. And this ring has some other descriptions, or has another description. So z hat factors as a product of the p-adic integers over all primes p. There's something similar you can say about this ring of finite adels. It sits inside the product over all primes p of the p-adic rational numbers. But it's not the entire product. It's what's called the restricted product, meaning you only get those sequences of p-adic rational numbers where all but finitely many terms are integral. And there's only finitely many primes which can appear in the denominator of a fraction. So this ring of finite adels is a place where the coefficients of both b and a can be considered to live. So this composition makes sense as a matrix over the ring of finite adels which preserves the quadratic form q. We get this element in this orthogonal group, but it depends on some choices that we've made. Right? This matrix B, it was chosen to be any matrix GLNQ that converts q prime into q. So that's ambiguous up to right multiplication by matrices that preserve the quadratic form q. And that ambiguity shows up as an ambiguity of this product. This is ambiguous up to multiplication on the left by elements of OQ of the rational numbers. Similarly, A was just chosen to be any matrix with coefficients in Z hat that converts Q prime into Q. And that's ambiguous up to right multiplication by elements in OQ of Z hat. So this B inverse composed with A, it's well defined not as an element of this group, but as a double coset. It's well defined modulo left multiplication by elements of OQ of the rationals and right multiplication by elements of OQ of Z hat. Now what can we say about this double coset? Well, what would it mean to get the identity double coset here? What that would mean is that it's possible to make clever choices of B and A in such a way that this product is actually equal to 1 inside this group here. In other words, it's possible to arrange that A is equal to B. And what does that mean? Well, the coefficients of B lie in the rational numbers, and the coefficients of A lie in this ring Z hat. And if you look at their intersection inside this ring of finite adels, that's just the usual ring of integers. So if you can arrange that you get the identity double coset here, or sorry, if you do get the identity double coset, it means that you can arrange that A is equal to B, which forces them both to have integer coefficients, which means that you've succeeded in proving that Q and Q prime are equivalent. Now, if you take that argument and go through it a little bit more carefully, it actually proves something stronger. What it proves is that this collection of double cosets is in bijection with equivalence classes of quadratic forms in the genus of Q. If you regard Q as fixed, so this set is fixed, then the construction, which starts with Q prime and makes this double coset, well, gives you a bijection between the equivalence classes of possible Q primes and the set of double cosets. So what's the upshot of that? Well, the Siegel mass formula is about counting the number of double cosets. A priori, it's about counting the number of quadratic forms in a genus, and it can be converted into a problem of counting the number of double cosets. So let's start thinking about it that way. So before we go on, there's one maneuver that I would like to make that will make this next part make sense. And that's that I would like to replace this ring of finite adels, which has to do with the product of all the p-adic completions of the rational numbers, by the ring of all adels, which is a similar product, but you include all the completions of the rational numbers. So let me just make one further definition. The ring A of adels is what you get when you take the ring of finite adels and just cross with the real numbers. And what I would like to do here is replace the ring of finite adels by this larger ring of all adels. Now if I do that, of course, I make this group much bigger. I include an auxiliary factor of OQ of the real numbers. And OQ of the real numbers, remember, is this compact Lie group of rotations in Euclidean space. So I don't want to change my double cosets, and I'm going to account for making the group in the middle bigger by just dividing out by that extra slack on the right-hand side. You divide out by OQ of Z hat cross R. Okay, so the next ingredient in the story is the observation that these groups have a lot of structure that you can exploit. So this ring of adels is not just a ring, it has a topology on it, which makes it locally compact. So this is a locally compact commutative ring, and if you look at OQ of the adels, this is some set of n by n matrices satisfying some conditions. This inherits a topology which makes this into a locally compact group. And there's two subgroups of this that we're interested in. There's this subgroup of OQ of z hat cross R. With respect to this topology, this subgroup is open and also compact. And there's also OQ of the rational numbers. And this subgroup is closed and gets the discrete topology. This is a discrete subgroup. And this statement here would not be true if I hadn't well, I guess actually it would be okay in this case because the real part is compact. Anyway, we're going to work with all these terms. Okay, so let's exploit there are things we can do with locally compact groups. So OQ of the Adels, by the theory of locally compact groups, has a Haar measure. U. So any locally compact group has a left invariant measure, and sometimes you get lucky, and it's both left and right invariant. And this is one of those cases. This actually has a left and right invariant measure mu, which is well defined up to scaling. And the fact that this is left invariant means that it descends to give you a measure on O cubed mod the action of this discrete subgroup. So this inherits a measure, which I'll also denote by mu. Now we're interested in this collection of left cosets once you mod out further by a right action of OQ of z hat cross R. And we're interested specifically in how many double cosets there are. And here's your naive guess for how many double cosets there are, which is that the size of this collection of double cosets OQ z hat cross R Q would just be given by the measure of the space that you're acting on, OQ of the Adels mod the rationals, divided by the measure of the group that's acting. Right, this is a sensible thing to write down because this subgroup is actually compact and open. So when you restrict mu to this subgroup, you get something of finite measure. So this is a naive guess, and this would be right if this group was acting freely on this collection of cosets. Right? The number, what we're trying to do is, let's say it this way. If you compute the measure of this quotient here, what you get is the sum over all orbits of the measure of that orbit. And the measure of each orbit is just the measure of this group that's acting divided by this, the size of the stabilizer group of that orbit. Those stabilizer groups are finite groups, and they're exactly the finite groups that show up in the definition of the mass of Q. So this naive guess is wrong because this action is not free, but the non-naive version, let's say the correct statement, correct guess, is that this quotient is measuring the sum over all Q prime in the genus of Q of 1 over the size of OQ prime of Z. In other words, this is what I called earlier the mass of Q. So the mass of Q has this expression as a ratio of 2 volumes. And in order to make sense of this, you needed to choose a Haar measure on this group OQ of the Adels. Now, that's not unique, but it's almost unique. Haar measure on a locally compact group is unique up to scaling. And that's okay in this expression because you'll note that mu appears in the numerator and the denominator. So if you scaled mu by a constant, this expression on the right-hand side wouldn't change. But the fact that mu is ambiguous up to a scalar means it doesn't make sense to try to compute these numerators and denominators independently of one another. Those are ambiguous up to a scalar. So I'd like to introduce one more modification in the story, and that's to replace the orthogonal group by the special orthogonal group. So in what follows, I'm going to write SOQ of a commutative ring R to mean the collection of matrices that preserve the quadratic form Q and also satisfy the condition that the determinant of A is equal to 1. So you can equip SOQ of the Adels with a Haar measure, and mod out by this discrete subgroup, take the measure and divide by the measure of SOQ of Z hat cross R. And this quantity is actually slightly different from the quantity that you would get if instead you used the full orthogonal group, but it's just off by a factor of 2. So this is actually twice as big as the mass of Q. Now the reason that I want to do this is because for the special orthogonal group something unexpected happens, which is this locally compact group actually has a canonical Haar measure. There's a canonical way to normalize the measure on that locally compact group. That canonical measure is called Tamagawa measure. So I want to now explain to you what Tamagawa measure is. So let's look at SOQ of the Adels. And how can you think about this group? Well, it sits inside SOQ of the real numbers cross the product over all prime numbers P of SOQ of the p-adic rational numbers. It sits inside, again, as what's called the restricted product, where you're only allowed to have denominators in finitely many places. So if you wanted to put a measure on SOQ of the Adels, you might start by trying to put a measure on each of the factors appearing in that product decomposition. So let's start with the familiar object, which is SOQ of the real numbers. Remember, this is a compact Lie group. In particular, it's a manifold. And if you want to choose a measure on a smooth manifold, one way to do it is to take a differential form of top degree. And if you want to write down a left invariant measure on this manifold, it'll suffice to choose a differential form of top degree that's also left invariant. So on this compact Lie group, you have a vector space V that I'll denote by VR, which is the space of left invariant top forms. This is a one-dimensional vector space over the real numbers. And if you choose any non-zero vector in here, it determines for you a Haar measure on this group. Okay, so that's an explicit way to get Haar measures, but it hasn't cut down the ambiguity at all, because this is still ambiguous, now up to scaling by any non-zero real number. But we can cut down that ambiguity a little bit by observing that this compact Lie group is not arbitrary. It actually comes to you in a very specific way. It comes to you by this formula here, which is expressing it as an algebraic group. So SOQ, let's say, of the real numbers is the collection of all A in GLN of the real numbers, such that the determinant of A is equal to 1, and Q composed with A is equal to Q. So this is an example of a linear algebraic. It comes to you as a collection of n by n matrices that satisfy some equations that can be written as polynomial in the coefficients of the matrix. So a consequence of that is that this SOQ of R makes sense as an algebraic variety over the rational numbers, and you can contemplate differential forms on that algebraic variety in the sense of algebraic geometry. And because that algebraic variety is defined over Q, well, inside V sub R, you have this one-dimensional rational vector space, which are, let me say, these are the algebraic differential forms. Algebraic and left invariant differential forms on SOQ, thought of as an algebraic group So that's a nice observation because it cuts down the ambiguity a little bit, right? Now, any non-zero element of VQ is in particular a non-zero element of VR, and therefore gives you a Haar measure. Now it's only ambiguous what that Haar measure is up to scaling by a rational number. Okay, so that's the story for SOQ of the real numbers. What about one of these groups like SOQ-QP? So this is not a Lie group in the usual sense, but it's an example of what's called a p-adic analytic Lie group. And there's a similar story for p-adic analytic Lie groups. So there's a notion of differential form on this object. There's a space of left invariant differential forms, which is a one-dimensional vector space, now not over the real numbers, but over QP. And every non-zero element of this one-dimensional vector space will determine for you a Haar measure on this group. But just as in the Archimedean case, there's more structure here, because this p-adic analytic Lie group is described in the same way. It's the collection of n by n matrices that satisfy certain polynomial conditions. It comes from an algebraic group defined over Q, and therefore every algebraic differential form on that group gives you a p-adic analytic differential form. So this vector space VQP also contains a copy of this vector space VQ. So what's the story? If you choose any element, let's call it omega, which is different from 0, in this vector space VQ, then we can say omega determines a measure, let's call it u omega comma p on SOQ-QP and u omega infinity on SOQ real numbers. And Tamagawa's idea was to take all these measures and multiply them together. So roughly speaking, you define a measure called Tamagawa measure. Now on this group SOQ of the Adels, and let me just put it in quotation marks, you take the product of u omega p and let's say u omega p. Just take the product of all the measures that you get from these constructions that you can do at each place. Okay, so I put that in quotation marks because there are some things to check to make sure it makes sense. Right? It's given sort of by an infinite product. When you write an infinite product, you have to worry about whether or not it converges. And this infinite product does converge, but an analogous construction, if you use the entire orthogonal group rather than the special orthogonal group, would not converge, which is why I wanted to shrink these groups down. Another question that you could ask is this actually independent of omega? Or does it depend on a choice? It actually is independent of omega. And to see that, I want to consider what would happen if you took this omega and multiplied it by your favorite non-zero rational number, let's say -5. So you multiply omega by -5, what happens to each of these local measures? Well, first, what happens to the measure that you get on this compact Lie group SOQR? So you have a differential form on this manifold, and you multiply it by -5, what happens to the corresponding measure? Well, it just gets multiplied by the absolute value of -5, meaning the measure gets 5 times as big. Now, if you ask what happens in the p-adic case, it's exactly the same thing, with the caveat that it's not the usual absolute value of -5, it's the p-adic absolute value of -5 that you have to multiply by. That means that for all primes that are different from 5, you don't change the measure at all. The only thing that happens is when p is equal to 5, and in that case, your measure gets 5 times smaller. So once you multiply all these things together, it turns out that it didn't matter that you scaled omega in at all. So this Tamagawa measure is a canonical measure on SOQ of the Adels. And well, here was a story that we told using any measure. Now let's use the canonical one. So you can take the Tamagawa measure of twice the mass of Q. The version with the special orthogonal group reads as something like this. And what you can say is that the mass of Q has some expression where there's a numerator and a denominator that are both expressed in terms of Tamagawa measure. Now this denominator is actually something you can explicitly evaluate. And that's because this group SOQ of Z hat cross R, it's not a restricted product, it's actually literally a Cartesian product of an Archimedean factor, which is this compact Lie group, SOQR, and a product over all primes P of SOQ of ZP. So if you want to evaluate the denominator, you just go through that procedure that I described. You choose your favorite differential form, and then you compute left invariant differential form. You compute the volume of SOQ of the real numbers in terms of that differential form. You'll see something that involves volumes of spheres multiplied together. And then you compute the volumes of these things. These are profinite groups. Computing volumes is really a counting problem that you have to consider for every prime P and multiply all the answers together. And when you do that, you're going to see things involving the Riemann zeta function up here. So it turns out that all of the complexity in the original statement of the Siegel mass formula that I gave you came from evaluating the denominator of this expression. And you can reformulate the mass formula as a statement which is just about the numerator. So let me tell you that reformulation. Formula, I'm going to say Tamagawa-Bay version. And what this says is that if you take the Tamagawa measure of SOQ of the Adels, modulo this discrete subgroup SOQ of the rational numbers, that this is equal to 2. So this statement has some advantages over the one that I gave you earlier. One is that I don't have to look it up every time I give this lecture. This one is easy to remember. Another is that the formula that I gave you earlier was specific to the case of a unimodular quadratic form. This is not, actually. This is a formula which is correct for any quadratic form, let's say at least 3 variables. It doesn't have to be unimodular. It doesn't have to be positive definite even. So it's some analog of the mass formula that makes sense even when the mass formula's counting interpretation becomes a little murkier, let's say. But you still might complain that there's something mysterious here, which is what's up with this random quantity on the right-hand side? Where does the number 2 come from? Turns out that the number 2 comes from the fact that the special orthogonal group is not simply connected. The special orthogonal group associated to the quadratic form Q actually has a double cover, which is called the spin group associated to the quadratic form Q. And the construction of Tamagawa measure makes perfect sense for the spin group as well as the special orthogonal. So you can also contemplate the Tamagawa measure of spin Q of the Adels modulo spin Q of the rational numbers. And if you were to do that, you would actually get 1. And these two statements shouldn't be obvious, but they turn out to be equivalent to one another. First, in the sense that they're both true, but also in the sense that it's much easier to deduce one from the other than it is to prove either one individually. So this is a sort of reformulation of the mass formula using this notion of adelic volume. And motivated by this, they made the following conjecture. And the conjecture is that something like this should not be special to the fact that you're talking about spin groups. It should be true for any simply connected group. So let G be a simply connected semi-simple semi-simple algebraic group, maybe I should say bigger than semi-simple maybe, algebraic group over the rational numbers, meaning something that's described as a subset of GLN cut out by polynomial equations where the coefficients of those polynomials are rational. Well, in that case, you can make sense of G of the Adels, which is a locally compact group, and Tamagawa's construction gives you a canonical Haar measure on that locally compact group. And that has G of Q sitting inside as a discrete subgroup, and you can contemplate the Tamagawa measure of the quotient. So this quantity is sometimes called the Tamagawa number of the group G. And the conjecture is that if your group is simply connected, that this should always be equal to 1. And in the case of the spin group, this conjecture is essentially the Siegel mass formula. So this conjecture is now a theorem. It was proven by Weil himself in many cases, so Weil did many examples of this. So let's say this was proved for split groups by Langlands, for quasi-split groups by Lie, and for general groups using a trace formula argument by Kotlitz. So how much time have I got left? 7 minutes. So let me tell you now what this series of lectures is going to be about. So this is a statement about an algebraic group over Q. Q is a number field. And in number theory, there's an analogy between number fields. A number field is a field that's a finite extension of Q. And what are called function fields. Function fields are fields that are finite extensions of things that look like a finite field adjoin one parameter x. So there's an analogy between these kinds of fields, and the questions that you can make sense of for number fields, you can typically also make sense of for function fields. So for example, if you have a semi-simple algebraic group defined over a function field, you can also first define a notion of Adels. You can define what you mean by G of the Adels. It's a locally compact group, and you can make sense of Tamagawa measure. There's a canonical measure on that locally compact group. And so you can contemplate this same question. What happens when you take the Tamagawa measure of this quotient? And the typical behavior of questions like this is that the number field questions are much harder than the function field questions. Questions about function fields have a relationship to algebraic geometry that you can exploit, that you can exploit to good effect. You can often prove things for function fields that, like the Riemann hypothesis, which are considered, very difficult in the case of number fields. So this Weil conjecture about Tamagawa numbers was sort of an unusual exception to this, in the sense that it was a statement which was known over number fields before it was known over function fields. And so my goal over the next few lectures is to sketch some joint work with Dennis Gates-Gorey, giving a proof of the analog of Weil's conjecture in the function field case. And so let me just say something about what will happen in each individual lecture. So lecture 1 we just listened to was this motivation, an explanation of what Weil's conjecture is about in the number field case. So lecture 2 is going to be completely unrelated to that. So lecture 2 I'm going to talk about something that I'll call non-abelian Poincare duality. So this is going to have nothing to do with number theory. It's going to have nothing to do with algebraic geometry. It's going to be a story really in topology about what happens when you try to contemplate Poincare duality, which is a phenomenon that you have in the homology or cohomology of a manifold, and try to extend it to the case where you take cohomology with non-abelian coefficients. So I'll tell you the story in topology here, and then the remaining 2 lectures, I want to connect this non-abelian Poincare duality with Bayes' conjecture. So in lecture 3, I'll spell out, say I'll explain what Bayes' conjecture says in the function field case. And explain how it's something that you can relate to questions about the cohomology of certain moduli spaces of bundles. And in lecture 4, I'm going to sketch for you a proof of that Bayes' conjecture in the function field case using this notion of non-abelian Poincare duality, or more precisely, using an algebro-geometric version of Poincare duality, non-abelian Poincare duality, which I will describe for you. All right, I think I'm just about out of time, so I will stop there. Thank you.
Do we have any questions for our speaker?
In the function field case, did you reformulate things using values of
Using
values of data? The original math formula, you have these values of data.
I mean, there's things that look like L functions that appear in the proof, but they're not really important to the structure of the proof. I mean, they're not. Let me say I don't know exactly how to answer that.
Yeah, in more general case, the general case, we cover something like a quadratic form or some other variant.
Yeah, so in lecture 3, I'm going to spell this out in more detail. But what I did in this lecture was I started with something concrete about counting quadratic forms, and I converted it into this abstract statement about volumes of groups. And the abstract statement has the virtue of being succinct. I'm saying something is equal to 1. So what I'll do in lecture 3 is go in the other direction. So I'll start in the function field case with this abstract statement that some volume is equal to 1, and I'll explain how you can translate that into a concrete counting problem. But what you're counting there are not quadratic forms. Instead, they're principal bundles with respect to a group.
Questions for our speaker? Let's thank him again.